In our next example here, we have an observer on a cliff that's 360 meters above sea level and has an angle of depression, which means looking from the horizon down, of 28 degrees. We want to know what the horizontal distance is between the ship and the observer. So we're talking about an angle, we're given the side that's opposite, and we're looking for the side that's adjacent. When I set up my equation, I will have, since I'm working with the opposite and the adjacent, that the tangent of my angle, which was 28 degrees, should be equal to the opposite side, 360, divided by my adjacent, which was called d. I type in the tangent of 28 degrees into my calculator, and I see that that yields 0.5317, and that's still equal to my 360 divided by my d. Since the variable is on the bottom, I know that I take and I divide that 360 by the 0.5317, and that means that my distance, the horizontal distance that is going to be equal to 677.06, and this time we're in meters. Again, these are just practical examples in word problems for the things that we already learned in 12.1. In this next example, we have a pilot at an altitude of 2 miles. He observes a control tower at an airport. It's 7 miles from a point directly below the airplane to the control tower. And we want to know what is the angle of depression. So the angle of depression, remember, is from the horizon down, so that's this angle A. We're given the side that's adjacent and the side that's opposite to that angle. That means that I'm dealing with tangent. So as I set up my equation, I will have the tangent of my angle A equals the opposite side to that, which was 7, divided by the, which was 2, divided by the adjacent side, which is 7. And hey, surprise, surprise, we have that this is an angle that we're looking for, so that's where we have to use the second button. So I know that my angle A will be equal to second tangent of 2/7, and that means in the end I get 15.945 degrees after I hit the enter button. Let's try another one. Lots of examples. In this next example, a sonar operator on a cruiser detects a submarine 500 meters away from it at an angle of depression of 37 degrees. How deep is the sub? So now I have an angle of 37 degrees, angle of depression from the water level down to the sub. I know that I'm looking for the side that's opposite to that angle of 37 degrees, and I have the hypotenuse given to me, which was the distance to the sub directly. When I see an angle, the side opposite and the hypotenuse, I automatically think of the sine. So I know that the sine of 37 degrees is equal to the side opposite of that angle divided by the hypotenuse. And I set up my equation. I can now type in the sine of 37 degrees. When I do that on my calculator, I get 0.6018, and that's equal to my h over 500. And then, to find my h, since the h is on the top, I know that my h will be equal to that 500 times 0.6018, which yields a grand total of 300.91, and we're in meters. Or in other words, the depth of the submarine is 300.91 meters, roughly 1,000 feet. In this next example, we have a flagpole that is 8.06 meters high and casts a shadow of 11.1 meters. And we want to know what is the angle of elevation. So elevation means looking up to something, or from horizontal up. In this case, what that's talking about is this angle right here, angle A. And we have, from the reference of angle A, the side that's opposite to it and the side that's adjacent to it. And when we're working with those kinds of things with opposite and adjacent, we know that we have tangent. So that means that the tangent of angle A is equal to the opposite side divided by the adjacent side. Surprise, surprise, we're talking about finding an angle. So I know that my angle A will be equal to the second, because we have to use that second button to get to the inverse, tangent, because that's the function we're working with, and then I type in the fraction that I need, which was 8.06 divided by 11.1. And after I hit enter, I find out that I get 35.984 meters as the angle of elevation. Let's try a couple more. Let's find the length of the shadow of a building 400 feet tall when the altitude of the sun is 49 degrees. When they say the altitude of the sun, they mean the angle of elevation when you're looking up towards the sun. So now I have an angle 49 degrees. I know that I'm given the side that's opposite to that, which was the height of the building, and I'm looking for the adjacent side, which was the shadow. When I set up my equation, knowing that I'm working with an opposite and an adjacent side, that means that I will have the tangent of that 49-degree angle is equal to the opposite side, 400, divided by the adjacent side, S, for shadow. I type in that 49-degree tangent into my calculator, and I see that I get 1.1504 for the tangent of 49 degrees. Remember to be in degree mode. And that should be equal to 400 divided by that S. Now, since the variable S is on the bottom of the fraction, I know that that means that I will have that the S is equal to that 400 divided by 1.1504. Or in other words, my S is going to be 347.705 feet. This is the shadow length cast by the building. One more problem. In our last problem, there are multiple things being asked here. We have a diagonal being drawn across a football field. It's 155 feet wide and 320 feet long. And we want to know first what size angles will be made with the sidelines. Now, the sideline angles we know are angle A, the sidelines. So this means that I'm working with angle A, and I have the side opposite to angle A being 150, and the side adjacent to angle A being 320. When I see that I have an angle that I'm looking for, and an opposite side and an adjacent side, that means I'm working with tangent. So I set up that my tangent is equal to 150 over 320. When I do second tangent of 150 divided by 320, I find my answer to be 25.12. Remember, that's in degrees. What about if I asked, what are the angles it's making with the end lines or the touchdown line kind of thing? That's the other scenario. That's talking about when you're talking about angle B, because that's the one that's next to the end lines or the end zone kind of stuff. So now, with reference to angle B, it looks the same for the most part, but everything's flipped around because the side that's opposite to angle B is 320, and the side that's adjacent is 150. So this time, highlighted down below in orange, I have the tangent of angle B is the 320 over the 150 instead of the other way around. And when I do second tangent of 320 over 150, I find out that that's a 64.89 degree angle. And this kind of makes sense because the two of them should add up to 90 degrees, give or take a hundredth, because you might be off in your rounding just a little bit. The final question in part C asks about how long is the diagonal. Now, the diagonal that I'm looking for is the one that's lined in red now. And for this one, really, I'm going to use the Pythagorean theorem. So the diagonal is called h, and for hypotenuse in my estimation. So that means I have leg squared of 150 plus leg squared to the 320 should be equal to the hypotenuse squared. And so you can type these into your calculator. They're huge numbers. Just don't forget in the end, since you're looking for h, to take the square root. When you get done, you should get an answer of 18.8. Give that a shot, see if you can do it. Basically, this whole section 12.2 was a using of the information we learned in 12.1, which was basically sines, cosines, and tangents, and how do you write down the relationships of those, SOHCAHTOA, and then putting them in the context of word problems and using those same concepts.